In section 3.2, we learned two more rules of differentiation. Essentially, all the rules that we are learning are stemming from the definition that came from chapter 2, and now we're getting some things that help speed up the derivative process. So the first rule that we learn is called the product rule, and this is just giving us a way to take the derivative of a product of two functions. So if f and g are both differentiable, then the derivative with respect to x of f of x times g of x is equal to f of x times the derivative with respect to x of g of x plus g of x times the derivative with respect to x of f of x. I sometimes think of this in a shorthand way. We have functions of x, and we are also already saying that we're taking the derivative with respect to that independent variable x. So we can just write the derivative of the product f times g is just f prime g plus g prime f. You can think of this as the derivative of the first function f times the second function g, and then plus the derivative of the second function g prime times the first function f. The quotient rule is somewhat similar, but with some variations. So again, if f and g are differentiable, then the derivative with respect to x of the quotient f of x divided by g of x becomes g of x times the derivative with respect to x of f of x, and now minus f of x times the derivative with respect to x of g of x, and then all divided by g of x squared. And again, we can think of this in a shorthand way as the derivative with respect to x of the quotient f divided by g. That will just be f prime g minus g prime f, all divided by g squared. I also sometimes think of this as just, well, the top part of a fraction and the bottom part of a fraction. So derivative of the top times the bottom, and then minus the derivative of the bottom times the top, and then divide all of that by the denominator, or the bottom part of the fraction, squared. So let's see how this works just in one example. Number 20 on page 188. Here we want to differentiate the function y equal quantity z squared plus e to the z times the square root of z. So we have a product, but let's also note that the independent variable this time is z. So by implication, when we say differentiate, we are going to be looking at y prime of z, taking the derivative with respect to z. So y prime of z is what we want to do to this. We will need the product rule because we will have a product from this, but another good idea to do before you jump into the product rule is see if you can actually simplify things by just multiplying first. And one thing that we can notice is that we've got a power of z inside the parentheses, and then also on the outside, because the square root of z is the same thing as z to the 1/2 power. So it might be easier if we multiply first, because then we'll have a power of z, which in this case will be z to the 2 plus 1/2, which is really 5/2 power, plus z to the 1/2 times e to the z. And this time, in this product, we are going to need the product rule. So this simplifies this a little bit in the fact that we won't have to be taking the product rule too large. We can just use power rule for this, z to the 5/2, and then use the product rule for the second part, z to the 1/2 times e to the z. So y prime of z will be the derivative with respect to z this time of z to the 5/2 power plus z to the 1/2 times e to the z. And again, we can distribute our derivative just like we saw in section 3.1, the derivative with respect to z of z to the 5/2 power plus the derivative with respect to z of z to the 1/2 times e to the z. Now this is a product, so it might be helpful if we just identify the two things that are being multiplied, and then we can also use some of the notation from the product rule, and we can call f z to the 1/2 and g e to the z. Continuing with the first part, again, we just need the power rule here, which means drop the power 5/2 down as a coefficient, and then that gets multiplied by z, now raised to 5/2 minus 1, which is 5/2 minus 2/2, or 3/2 power. So that finishes that part. But then the next part, I'm going to just remind us that this will be f prime g plus g prime f. So in that case, what that means with the functions that we have called f and g, f prime is just the derivative of z to the 1/2, which is 1/2 z to the negative 1/2. We drop the power 1/2 down, and then we subtract the power by 1. Positive 1/2 minus 1 gives us negative 1/2. And then we multiply this by e to the z. And then g prime, if g is e to the z, the derivative of the exponential function with the natural base e, that's just itself. So it's just e to the z. So now we've finished all of the derivative process to this. And we can simplify. I would recommend just leaving things as they are, mainly because it's in the simplification process that some algebraic mistakes can happen. Also, we are going to be more interested in doing things with these derivatives, like maybe finding the second derivative. We can handle all of that stuff in problems when asked. When we are just asked to differentiate, we can leave things like this. I will say, on WebAssign, if you are told to write things using positive exponents, make sure you're doing that. I'm not going to be asking you to do that, so what I have boxed here is an appropriate answer for me. Okay, let's look at another problem, this time using the quotient rule. Number 14 on page 188. Here we would like to differentiate y equal the quotient square root of x divided by 2 plus x. This time around we have the independent variable is x, so of course we are going to be taking the derivative with respect to x. So y prime is just the derivative with respect to x of the quotient square root of x all divided by 2 plus x. So now, again, it might be helpful if we just name the numerator f and the denominator g, so that, again, we can remind ourselves that this will just be the derivative of the top, so f prime g, and then minus g prime f, and then all of this divided by g squared. So then we should write down what our derivatives are. So again, if f is equal to the square root of x, remember that's equal to x to the 1/2 power, which means that f prime, just like we saw in the previous example, is 1/2 x to the negative 1/2. And then if g is 2 plus x, then g prime is just the slope of that line, which is 1. Notice here we are focusing on the quotient rule, so I don't really need to be as laborious in showing my work for the sum rule. And also, we do want to start getting used to that the derivative of a linear function is just the slope of that line. So in this case, g prime really is just the number 1. So now we can plug all of this in. F prime 1/2 x to the negative 1/2 times g. G is the function 2 plus x. Minus g prime, which is 1, times the function f. And I'm going to write that as x to the 1/2. And then all of this divided by g squared, which is the quantity 2 plus x squared. Now a hint with the quotient rule. Simplify the numerator. And also, don't multiply out the denominator. Leave it factored like it is. The reason why is if things can simplify in this fraction, it will be so because we have factored things in the numerator and denominator. So we really just want to combine like terms in the numerator and leave the denominator factored. Maybe then we can simplify. So for now, let's just multiply out what we have. 1/2 x to the negative 1/2, I'll multiply that by 2. 2 times 1/2 is 1, so that just leaves us x to the negative 1/2. And then 1/2 x to the negative 1/2 times x, I'll get 1/2. And then the powers add, so I get x to the positive 1/2. And then I have minus x to the 1/2. I can see that I can combine 1/2 x to the 1/2 minus 1 x to the 1/2, and I'll get a negative 1/2 x to the positive 1/2. And even if I did combine things or maybe do some factorization, I've got a negative between two terms in the numerator. I'm not going to be able to cancel anything out with the denominator, so this is good enough. I have simplified it, and I think that's a good enough answer. Anything further would start involving combining fractions or rationalizing denominators, and that's getting a little bit too much algebra thrown into this. So just leaving it like this is a good place. So then finally, I want to look at number 61 from our book on page 190, and this actually will set up something that we will learn in a later section related to what's called the chain rule. This sets forward a pattern that we start to notice, and it helps us understand why another rule that we will learn works in the way that it does. So first, use the product rule twice to prove that if f, g, and h are differentiable, then the derivative of the product of all three of those, f times g times h, is equal to f prime times g times h plus f times g prime times h plus f times g times h prime. And really what this is an example of is we've got a product of three things. We can use the associative rule to actually turn this into, let's say, f times the product g times h. So it's like we're saying we could just take the product of g times h first and then multiply that by f. And when we do that, this derivative by the product rule just becomes the derivative of the first function and then times the second function, which is g times h. And then we have to add the derivative of the second function, g h prime times the first function. All right, so we're using the same product rule. It's just that we're calling the second function, it's a product, g times h. And now we can see what's about to happen. I've got my f prime gh, which is the first part that we wanted. But now we need to find the derivative of the product g times h, which just means the derivative of g times h, and then plus the derivative of h times g. And all of that is in the square brackets that has to be then multiplied by f, which we then distribute into that sum, and we get f prime g times h plus, if we write things alphabetically, f g prime h plus f g h prime, which is exactly what we wanted in part A. So that's true. Okay, so that's how we could find the derivative of a product of three things. So now part B says, let's pretend or take f equal to g equal to h. Now show, so we're going to say f is equal to g is equal to h. Now show that the derivative with respect to x of f of x cubed, so what if you had f of x multiplied by itself 3 times, show that that's just equal to 3 times f of x quantity squared times f prime of x. Well, there's not really much to show here. We've already got that if you take the derivative of a product of three things, we've got a formula for it. So remember, f of x cubed is just the same thing as f times f times f. So the derivative of that is just f times f times f prime, which you can see what this is going to become, right? If you think of things as first, second, and third, which is why I wrote those things alphabetically, then really we're just going to have, okay, the first function, its derivative, f prime, and then times the second and the third. And then now I need to find the derivative of the second, which is really just f again. And it has to be surrounded by the first function and the third function. And then finally take the derivative of the third function and then multiply it by the first and the second before it. But these things all look exactly the same. I've got an f prime times two other f's. So I have three of those. And the two other f's are just f times f, which is really f squared, and then f prime is just f prime. And if we're using f of x notation, this is 3 times the quantity f of x squared times f prime of x. So now we've got a formula for how to find the derivative of the cube of a function. It just says that it's 3 times the function squared times the derivative. So we're going to use that to then answer this last part. Use part B to differentiate y equal e to the 3x. So part C, use part B to differentiate y equal e to the 3x. So if we're using part B, it means we do want to think of our function as the cube of a function. And e to the 3x is the cube of a function. It's the cube of e to the x. So then y prime is supposed to be 3 times the function squared. In this case, f is what's inside the brackets. So it'll be e to the x to the second power times f prime of x. And again, if f is e to the x, then f prime is also e to the x. And this just means that y prime is 3 times e to the 2x times e to the x, which is just 3e to the 3x. So later on in another section, we will learn that this is an example of what's called the chain rule. So we see that it stems from the product rule. And that's what we actually start seeing with a lot of these rules. They stem from one that came before and we get a new one. So we saw that with the power rule. And then we also see that with the constant multiple rule and how that relates to the sum rule. So the product rule starts to give some reasoning for why the chain rule is what it is.